the right experiments, and a number of other things. That's really Jeff in a nutshell. In addition to this, and this is really the coolest thing, Jeff can bend time. And why? Well, he's running a marathon. I think he's currently under 250. That's what I think is. But the real cool thing, which is relevant for me, is he came in my office and said, I can do this in 2 or 3 days. And this was, I can do a turbulence simulation in 2 or 3 days. It never really worked. I'm still waiting for some of the results, so I'm hoping that at some point he will be ending up with bending the time. That's really all I want to say here. Without further ado, I hand it over to Jeff.
All right, well, thanks for the introduction, Matthias, and I'll try not to bend any time during today's presentation. I'm going to be speaking today about hybrid modeling of engine core noise. So to begin with, we have to establish why aircraft noise or aviation noise is a problem. And as many of you are probably familiar with, when you hear airplanes flying overhead, the sound can be loud, it can be obnoxious, it can be disruptive. And if you're someone who lives, who works, who studies, or who sleeps in the vicinity of an airport, this can be really disruptive. It can adversely affect your quality of life over prolonged periods, and it's been linked to sort of to negative health consequences as well. So basically, people don't like living near these airports. They make for poor neighbors. And because of this, people who live in the vicinity of airports are generally opposed to airport operation. They try to limit the hours that these airports can operate. They try to limit, if anyone is proposing to introduce a new runway or new tarmac, they're generally opposed to airport expansion. And this is a problem given the current landscape in the commercial aerospace sector. So here in the United States, the number of passenger miles that are flown domestically is projected to double over the next 14 years. It's growing even faster internationally, and this in turn is taxing our existing airport infrastructure. So there's sort of 3 ways that you can deal with this problem. One is that you can build bigger planes, which we're starting to do, but we're hitting physical limits with. One is that you can continue to operate runways more efficiently, but to use that opening video as an example, and London Heathrow right now, you have to, for each runway, they need an airplane that's either landing or departing every 90 to 120 seconds. So we're running up against a physical bound there as well. Or the third thing you can do is you can lay new tarmac, but you really have to address this community opposition. Right here in Palo Alto, for example, there's a group known as the Palo Alto Sky Posse, which feels like we have too many airplanes flying overhead here in the Bay. They actually generously created this figure here, which shows that if you go out to Izzy's Brooklyn Bagels at the corner of California Avenue and Birch, and you just watch the sky all day long, you'll see about 254 planes flying below 10,000 feet overhead. So people find this disruptive. They try to reroute planes. They're opposed to expansion. Runway noise is a clear nuisance or a quality of life issue. In addition to this, if you're someone who works in very close proximity to aircraft, such as someone who works, for example, on the deck of an aircraft carrier, then exposure to these extreme sounds associated with aircraft can have really long-term perverse damages to your health. So it's estimated right now that the military spends on the order of about $1 billion treating just shy of 1 million personnel who are suffering from diminished hearing, from complete hearing loss, or from tinnitus, which is a high-pitched ringing of the ears. So this is a major problem for people who are working in the aerospace sector. Fortunately, all of these problems can easily be solved just by building quieter planes. But that in itself is quite challenging to do, and that's sort of the science topic or the research topic that I'm trying to address here. So if you consider an aircraft taking off, there are several different factors or several different systems that are associated with aircraft noise. You have the landing gear, which are particularly problematic, the slats and the flaps as well. But what we're going to be focusing on today are the engines. So engine noise is typically, it's so loud that it's considered sort of a distinct source from airframe noise. So we're going to be focusing on engine noise in this talk. So if you took the nacelle off that engine and you cracked it open, you would see that there are several common subsystems amongst nearly all turbojet engines. So you have a fan, a compressor, a combustor, a turbine, and then your nozzle and jet exhaust. And of these subsystems, there's sort of 3 primary noise sources that people consider. There's fan noise, there's combustor noise, and there's jet noise. Now, historically, people have identified fan noise and jet noise as sort of the 2 primary sources of aerospace engine noise. And borrowing a figure here from Andelling's review paper, what this is showing here is the noise that you would hear on the ground in this black curve. This is total engine noise as a function of frequency. So at very low frequencies, we can see here the jet engine noise, or the noise associated with high-speed jet exhaust, sort of our dominant noise source. And then fan noise, both broadband and tonal noise, dominates at higher frequencies. But over the past several decades, engineers have grown increasingly effective at reducing these 2 contributions to overall noise. And what's happening here is that by lowering this blue curve and by lowering this green curve, the black curve itself is starting to come down. But we have combustor noise sitting here in red in the middle. And if we continue to reduce the contributions associated with jet noise and fan noise, combustor noise is poised to act as sort of a tent pole here, or a limiting factor that will prevent further reductions in sound. And it's because of this that my doctoral work, or my talk today, is going to be focused on the problem of combustion noise, or of core noise, as it's known. So formally, core noise refers to any noise generated by an aircraft engine whose source is located within the body or the core of that engine. But it's commonly understood in the aeroacoustics community that combustion is the dominant source of core noise, so I'll use these two terms interchangeably. Core noise, then, is divided into two different mechanisms that give rise to sound. There's direct core noise and there's indirect core noise. So direct core noise is very intuitive. This refers to sort of the acoustic fluctuations that are generated by the unsteady combustion inside a jet engine. So if you found yourself situated inside the jet combustor, direct core noise is what you would be hearing. These are the acoustic fluctuations. They're oftentimes referred to as self-noise. But there's also a second source of core noise, which is a bit subtler, and this is known as indirect core noise. So if you consider an unsteady flame sitting inside an aircraft engine combustor, it's going to shed different turbulent structures. There will be hot spots and cold spots. There will be vortical or turbulent structures that are shed off. And these structures then are going to convect out of the combustor, and they're going to be accelerated as they interact with the turbine and with the nozzle downstream. This unsteady acceleration is going to stretch these structures, and it's going to distort them. And this distortion process gives rise to additional noise, which we call indirect core noise. So just to sum this all up schematically, you have your aircraft engine combustor sitting here. You have an unsteady flame. It's going to give rise to direct noise, some of which will propagate downstream and be heard outside the exhaust. Some of it will reflect back and can lead to thermoacoustic instabilities. And then you also have all of these inhomogeneities, or these turbulent structures that are being shed by the flame. And these are going to get stretched and distorted and give rise to that indirect noise. So the outline of my talk is really going to follow sort of the life cycle of these noise sources. We're going to begin inside the combustor of a jet engine, focusing on direct noise generation as well as prediction or identification of these turbulent structures. Then we're going to kind of convect downstream into the turbine section, where we're going to talk about modeling techniques to account for how turbomachinery or downstream engine components interact with these structures generated by the combustor. And then lastly, in the final portion of my talk, we're going to talk about, we'll discuss how core noise can affect the downstream overall acoustic signature. So how it propagates out of the nozzle, through the high-speed jet exhaust, and then finally to you on the ground here at ISIS. So with that, we'll begin the first portion of the talk, focusing on what's going on inside the combustor, direct core noise, and structure detection. So in order to study the noise that's generated inside an aircraft engine combustor, we need to settle on a geometry that will generate some noise. And to do this, we picked the configuration known as the Kleinbrandkammer, which is the German word for small combustion chamber, that was originally studied at DLR Stuttgart and DLR Berlin, the German Aerospace Agency. We picked this device because even though this is a test stand or a laboratory combustor, it contains much of the physics that's representative of of the combustors that you would find in aerospace engines or in aircraft engines. In particular, it's a dual swirl methane air combustor, so it has the sort of the complicated flow structure that you would expect to see inside of a real combustor. It's operated at an equivalence ratio of 0.9, which is admittedly a bit richer than what we might encounter in typical commercial applications, but this ensures good stability of the flame and facilitates experimental measurements. So we felt that this was an adequate compromise. In addition to this, this device liberates about 20 kilowatts of heat, which given the size of this device means that the volumetric heat release of the device is comparable to what you might see inside of a business jet engine. And then lastly, installed downstream of the combustion chamber is a choked converging diverging nozzle. And what this means is that not only will this device generate direct noise, as we discussed, but it will also have this unsteady or this strong flow acceleration downstream, which will allow for indirect noise generation as well. So having fixed our configuration, I then start to replicate this numerically using large eddy simulation. To do this, I used the code CRIS, which I'm sure many of you here are familiar with. It's a fully compressible large eddy simulation code for reacting flows. Combustion is modeled using the flamelet progress variable approach, which is very standard for these kind of simulations. And then additionally, we apply a non-reflecting boundary condition at the exhaust so that we don't introduce any artificial reflection or any spurious numerical noise. What's really noteworthy about this computation, though, is that even though the Mach numbers inside a combustion chamber are typically quite low, in this instance, they're somewhere between Mach 0.05 and Mach 0.1, we simulated this device in a fully compressible manner rather than using a low Mach code. And what this means is that we not only resolve the hydrodynamic structures inside the combustor, but by agreeing to sort of absorb an additional computational cost, we also resolve the acoustic structure inside the combustor as well. So we ran this device, we allowed it to reach a steady state, and then we sampled the statistics so that we could validate this against experimental measurements. And what you can see here on the left is a video of the temperature field inside the combustor. We get this unsteady V-flame structure, which is exactly what was observed in both numerical and experimental studies of the geometry. So the flame structure here is reasonable. In addition to this, we can compare the hydrodynamic field that we obtained with simulation against experimental results. And you see that we managed to capture the strong inner recirculation bubble, or inner recirculation zone, which is characteristic of this device, as well as a weaker outer annular recirculation zone. So the flame structure and the spreading angle are quite reasonable. And given the experimental limitations in the PIV data, we felt like the matches in the velocity field were adequate, so that we were sort of adequately reproducing the physics or the behavior of this device. In addition to this, because our focus is on direct core noise, we wanted to look at tonal structures and make sure that we were predicting a reasonable acoustic field inside the combustor. So to do that, we can compare against two sources. First, there's experimental pressure probe data, which detects several key features in the spectra. You have a volumetric mode, an axial mode, and an azimuthal mode that are detected. But in addition to this, if you work in the aeroacoustics community, there's sort of a very well understood analytic problem, which involves sort of the standing modes or the mode shapes that you would encounter inside a pipe. So we can compare not only the frequencies that we observe experimentally, we can compare against not only these experimental frequencies, but we can also compare against analytic predictions of sort of where we expect this device to be oscillating or where we expect to see strong tonal structures. So to do this, sorry, I'm ahead of myself here. We applied the discrete Fourier transform to every point inside the combustor geometry. And then we can look at where we see pile-ups of spectral amplitude, and we can identify structures from this, and then compare the mode shapes against our algebraic predictions and the frequencies against experiment. And we came away with 4 key structures. So first, we have a Helmholtz mode, which is sort of a volumetric beating of the system. You can see there isn't really much mode structure to this. It's just the whole system breathing together. We detected this mode at 127 hertz. Experimentally, this mode was identified at 132 hertz, so the agreement was quite good since we have only a 10 hertz resolution. Additionally, we matched the structure, the frequency of the first standing axial mode inside the device, as well as the first sort of radial azimuthal mode at 4800 hertz. And we also detected the presence of a mode, sort of a standing mode sitting in the upstream plenum. And while there was no experimental measurement of available inside the plenum region, this agrees quite well with the analytic model of where we would expect this structure to exist. So we were pretty happy. We thought that we were detecting sort of the key features inside the combustor, or the key features of the acoustic field inside the combustor. But ultimately, the goal of this work, or the goal of this talk, is to look at the downstream implications of core noise, to understand how it affects people on the ground. So to do this, we tabulated data from this simulation. We imposed a sampling plane downstream of the flame region inside the combustor, and then we can sample the full hydrodynamic, acoustic, and thermodynamic field that's advecting through this plane. And we built a sort of a database, which will contain both the direct core noise, or these acoustic fluctuations, as well as these unsteady structures that give rise to indirect noise. To efficiently represent this, because we're dealing with on the order of about 1 to 2 terabytes of data, we decomposed these fluctuations, or we decomposed these structures using proper orthogonal decomposition, or POD. So our reconstructed signal looks something like this. It consists of a global space-time mean. This is, if you're modeling the system thermodynamically, this is sort of the 0D state that you would see at the exit of the combustor. In addition to this, you have a steady, a temporally steady profile. So for example, this would be like Couette flow for the velocity field inside a pipe. And then we have these varying structures, which can give rise to indirect noise, which contain the acoustics. And this is really what we're interested in. So we have radial mode shapes, and then spectra describing how they're varying. To show you sort of qualitatively what this procedure looks like, we extract this steady mean here, so Couette flow, or whatever the sort of the baseline field of the combustor looks like in the exit plane. And then we have these unsteady structures that are sitting on top of it. We can take the mode shapes that are identified by POD and then project this unsteady structure onto it. And this in turn gives us a frequency spectrum, which is describing sort of how these modes are oscillating in time. And then for the time being, we're just going to table this database, but we're going to use this ultimately to study the downstream effects of core noise. So we'll come back to this in the third portion of the talk. But now moving downstream from our combustor into our turbine stage, we come to the second portion of the talk, where we're going to discuss low-order modeling of indirect noise, or sort of what is the effect of turbomachinery or the nozzling process and these unsteady fluctuations that we detected inside the combustor. So just to reorient you, we're now moving downstream here, and we're trying to assess the impact of this stretching or this distortion process associated with indirect noise generation. And it turns out that the existing literature on core noise suggests that this indirect core noise phenomenon, or this sort of downstream implications of combustion, give rise to more sound than you would see from, than you would expect from what's observed inside the chamber itself. So this plot here, which is reconstructed from Lako's model, shows you that depending on, so inside a combustor, you're typically going to exit the chamber at a very low Mach number, which we can approximate as being essentially Mach 0. And then at the engine exhaust, you're going to accelerate to sort of a transonic Mach number near 1. And what we can see is that if we hold the inflow Mach number, the Mach number exiting the combustion chamber fixed at 0, and we vary the outgoing Mach number, the predicted sound associated with entropy noise or with indirect noise is much stronger than it is for direct noise. So for real aircraft engines, this indirect noise physics is more important than the direct noise physics. So we want to model this process, but unfortunately, it's very complex. It's a very high-dimensional space. So if we tried to apply high-fidelity models such as LES or even URANs to describe the implications or the effects of these structures advecting through, we'd have to, the computational cost of this would be prohibitive. So instead, what we do is we have these structures that we detected from the combustor, and we're going to idealize them now as a series of planar waves rather than representing their full structure. So we're going to replace these now with just standing waves. And then what's typically done in this field is that the geometry itself can be neglected as well. So people will idealize these turbomachinery systems or these nozzle systems as just sort of black boxes, and they'll focus on the relationship between the outgoing acoustic waves and the incoming perturbations. So typically, this physics or this model is described in terms of a transfer function, which is going to relate the amplitude of the outgoing acoustic wave over the amplitude of the incoming disturbance. And these disturbances, again, they can be entropic disturbances, which is basically temperature, hot and cold spots. They can be velocity or acoustic disturbances. You can send vorticity waves, et cetera. There's a variety of different sources of indirect noise. So the model that's most typically applied is referred to as actuator disk theory. This is basically just a linearized, this is a linear method, which is based on just linearizations of the conservation equations or sort of jump conditions that are applied over the device. And this method was developed by Sebastian Kandel in the 70s and has proven to be quite successful at predicting very low frequency noise inside aircraft engines. So the model looks something like this. You have your disturbances in terms of entropy, velocity, and pressure, and potentially vorticity as well. And then you just apply a matrix multiply to relate your ingoing disturbances to your outgoing disturbances. So as part of my PhD work, however, I sought to improve this model by incorporating additional physics. And I did this in two ways. First, I wanted to improve the fidelity of the model by accounting for geometric and frequency-dependent effects. So this is going to be an extension to acoustically non-compact systems. And then secondly, I also wanted to incorporate new physics or a new sound source, namely by identifying that fluctuations in mixture composition or in the equivalence ratio of your combustor can also give rise to this indirect noise. So first we'll talk about this acoustically non-compact model. But in order to appreciate what was done here, you first need to understand what it means for a system to be acoustically compact. So if you have a disturbance that's going to enter your device, that disturbance will have some characteristic length scale, which is a function of its frequency. And we'll call that length scale lambda. Similarly, your device, whether this is a turbine cascade or a nozzle, will have some characteristic length scale, oftentimes the chord, which we call L. And then we refer to acoustic compactness as the relationship between lambda and L. So if lambda is much greater than L, we say that the device is acoustically compact. And what this means is that effectively these disturbance waves don't see the effect of the geometry. They simply, the device is so small compared to the length scale of the wave that it can be treated as a discontinuity. And that's how original actuator disk theory is developed. We describe this ratio in terms of a Helmholtz number, which is a non-dimensional number relating these two scales. And a flow would be acoustically compact if Helmholtz number was near 0. So my goal then was to extend this to finite Helmholtz number. And to do this, we need to apply a few simple modeling assumptions. First of all, we're going to treat the flow as quasi-one-dimensional. We're going to model it. We're going to basically extract a base flow along a streamline. So you can see here, this would be a streamline passing through turbomachinery. Or alternatively, you can conduct a planar average here that'll follow the base flow in this streamwise coordinate system. Additionally, we assume that the Reynolds number is large so that we can neglect any viscous or turbulent effects. and any boundary layer effects as well. We assume that the disturbance amplitudes that are entering the cascade are quite small so that we can treat them as linear perturbations about the base flow. This is generally a very reasonable assumption in sort of all acoustic applications. And then lastly, to simplify the math, we assume that the base flow in turbomachinery applications where we have turning flow, we're going to assume that it turns like a solid body. And this facilitates a lot of the underlying mathematics. So at the end of the day, we end up now, instead of having these jump conditions or this matrix multiply, we instead have a boundary value problem system based on the continuity equation, the streamwise momentum equation, either the transverse momentum equation or a model for transverse transport. And then lastly, we just have an entropy transport equation as well. So we can develop this model. We have this system of boundary value problems. But there's also a very subtle detail in my model compared to existing models, which improves the fidelity. So if we consider this streamwise coordinate system here, flow moving along this black or this red line, it's typical that this base flow, because it's turning, is described in sort of a modulus orientation coordinate system. So you have a velocity vector of magnitude w bar and corresponding orientation theta bar, which describes your base flow. Now, we're going to sort of zoom in on this to appreciate the difference between this formulation and the previous formulation. So it's previously done if you have your streamline sitting here, you have your base flow w bar and theta bar, and then if you have some disturbance w prime that's sitting on top of this, we describe this, it's typically described in terms of w prime, which is a disturbance or a linear perturbation to the vector amplitude, as well as a theta prime disturbance to the vector orientation. In my formulation of the model, we treat this same problem differently, and we gain some important properties from this. So if we have the same disturbance vector, w bar plus w prime, we now treat it in terms of a two-component disturbance velocity. So we have a w prime disturbance, which is in the streamwise direction, and then we have this second disturbance, beta prime. I sort of ran out of letters while we were deriving this, which is going to describe the transverse velocity disturbance as well. And while this might seem like a subtle detail, it actually improves the properties of the model somewhat substantially. And the reason for this is twofold. First of all, if you were trying to model a multi-stage turbine, where say in your second or your third stage, your base flow might enter at your base flow may not enter the device perpendicular to the axis of the engine. The previous formulation or the previous model will give you a different result depending on the coordinate system that you're trying to predict the flow behavior in. So the new model is now rotationally invariant, which is a big gain in terms of properties. And the second thing is that there's no longer a need to linearize trigonometric functions. So even though this is still just a linear model or a linearization of the system, the linearization error is reduced because we're no longer trying to linearize a nonlinear function. So we gain a little bit of accuracy from this. So now we can apply it to a model flow to sort of understand the implications of this model. To do this, we take a high-pressure turbine design from STABE, which has been studied a lot in sort of the turbomachinery community. We use Fluent to generate a RANS base flow, which you can see here on the left. And then we extract the streamline shown here, which we're going to parameterize in terms of, we're going to make it a unit distance so that it runs from s equals 0 to s equals 1. And then all we need to extract from this base flow is a profile of the Mach number, which you can see here in the plot on the right. So now what I can show you is the response of the system to different types of forcing. So first, on the left-hand plot here, we consider an entropy or sort of a temperature wave that's entering the system. And we can see that the response, or the acoustic response, or the pressure wave that exits the device is a very strong function of the Helmholtz number, or the frequency at which this oscillation is entering. So if we applied the traditional acoustically compact model across the whole range of frequencies, we would have this black curve up here. Whereas now that we're accounting for these geometric effects, or these frequency-dependent effects, we start to get a more nuanced prediction at large Helmholtz number. And we see a similar result here for acoustic forcing. So this would describe the response of the system if you had a pressure wave entering the turbine. This would describe sort of how much that acoustic wave grows as it exits the device. And we can see again here that there's a relatively strong, say, 20 to 30% dependency on this Helmholtz number, even for very modest Helmholtz numbers of 0.1, 0.2, 0.3. So this is sort of, it's a relevant physics that we need to take into account. So to summarize the properties of this model, we now have a rotationally invariant model with reduced linearization error. Additionally, if we consider sort of the parameter range in which turbomachinery operates for both aircraft engines as well as standalone power generation, we can see that if we consider sort of the high end of frequencies associated with core noise and relatively large blade chords, we really start to creep into the range where this Helmholtz number becomes appreciable. So for very low frequency noise, if we're only considering 50 or 100 hertz disturbances, acoustically compact assumptions are valid. But as we sort of reach the higher end or the upper echelons of this range, this acoustic non-compactness creeps in, and it's not uncommon to encounter Helmholtz numbers on the order of 0.2, 0.3, 0.4, where these frequency effects really start to matter. So this is sort of our first addition to the existing canon of actuator disk theory. But then we also wanted to demonstrate a second effect as well. Namely, we wanted to demonstrate how compositional fluctuations can act as an additional source of indirect noise. So the motivation behind this is really a lot of novel combustor designs that are being debuted. What I'm showing here from Yamamoto's lab is it's known as a staged injection combustor. So you can see that you have a pilot flame and fuel injection going on here in the yellow. And then you also have a second source in this blue region here where you have additional fuel being injected. Now, these combustors operate very unsteadily, and while we idealize them as being perfectly well mixed, realistically that's not always achieved. So if we have this staged injection, it's quite likely that the fuel-air mixture is going to vary as this device operates unsteadily. In addition to this, there's been a lot of development into so-called dual fuel combustors, where we're injecting not one but two different types of fuels, and this also can lead to unsteadiness or variations or fluctuations in mixture composition. So if we have fluctuations in mixture composition due to these multi-component effects, we're correspondingly going to have fluctuations in density. And as soon as you have fluctuations in density, you have the potential to give rise to additional sound. So to sort of briefly describe our modeling framework or how these compositional fluctuations can give rise to sound, what we're going to consider here is, again, just these sinusoidal perturbations entering, in this case, an acoustically compact nozzle. So I've developed the theory for both acoustically compact and non-compact devices, but we're just going to focus on the compact case here for simplicity. And we have this small mixture inhomogeneity entering the device. And what you can think about is sort of you're sort of instantaneously very rich, you're instantaneously very lean, you're fluctuating in time. And these fluctuations then are going to give rise to downstream sound. And we're going to focus on the relationship between this wave and that wave. So the math to this can get a little bit complicated, but basically we're going to apply these same jump conditions. We're going to assume that mass, enthalpy, and entropy are conserved, as well as the mixture fraction or the mass fractions of the species. Critically, the way that this model extends existing actuator disk theory are through these three terms in red here. So you have terms related to sort of the gradient in specific heats, and then you also have terms related to this psi here, which is a normalized chemical potential. So by accounting for these additional three terms, which are proportional to fluctuations in mixture composition, we can show that we're going to give rise to additional pressure fluctuations as well. And the way we describe this can be a little bit complex. So I'm going to show you sort of the axes of the figure here before we talk about the response itself. The most efficient way for us to plot this is to consider a nozzling system where we have flow entering at a very low Mach number into the nozzle. So it's going to enter the device at Mach 0. And then we're going to vary the Mach number that the flow exits the device. So this will range from subsonic to supersonic conditions. And our focus is really going to be on the sort of the transonic and the supersonic regime where aircraft engines operate. In addition to this, we want to consider the effect of equivalence ratio. So we're going to consider mixtures ranging from perfectly lean here on the left, phi near 0, all the way to stoichiometric mixtures, and then extending this on to rich mixtures on the right half plane. And then what we're going to show here is the logarithm of the acoustic response. So if we sent a unit wave in terms of mixture composition in, we're going to show the amplitude of the corresponding outgoing acoustic wave. And with that, we can finally reveal the data here. So we can see that the response here is a very complex function, both of how strongly we're accelerating the flow, as well as sort of what equivalence ratio we're operating at. So first of all, for subsonic conditions, we can see that the response here is on the order of, the log of the response here is on the order of -1. So we're only seeing like a 10% response to a unit compositional wave. This is very weak. This is sort of a regime where we don't expect this compositional noise to really have a strong impact on downstream sound. But as we approach transonic and supersonic conditions, we start to hit log 0 and then eventually log 1, where we see up to, say, a 10x response to a unit compositional wave. And what this means is that we're starting to generate some really substantial sound in response to these compositional fluctuations. In addition to this, we have some interesting features in the plot. We have this sort of zone of silence, or this silent line corresponding to the blue curve here. And then we also notice that the response is most pronounced in the lean regime. So this is very important for aircraft engine designers, because sort of this box right here from Mach 1 to equivalence with lean equivalence ratios is really the regime where aircraft engines are going to operate. So this suggests that this is sort of the regime where this mechanism is most sensitive or most likely to produce sound. And there are also control implications of this, because we can see that potentially if you operate at a slightly richer equivalence ratio, or if you stage your combustion, you can potentially suppress some of the noise just by shifting where you are laterally on this plot. So we demonstrated that compositional noise has a strong sensitivity, that we're going to generate an acoustic response to compositional perturbations. But we also want to assess how important this is inside a real aircraft engine environment. And to do this, we took some operating conditions that are sort of representative or characteristic of typical aircraft engines. So we're going to assume a relatively lean equivalence ratio. We can pull an adiabatic flame temperature from this. And then we can sort of model what our predicted intensity, what the predicted intensity of compositional fluctuations would be, and sort of the corresponding intensity for temperature fluctuations, or sort of traditional indirect noise. And what we see from this is that for subcritical conditions, we're not generating a lot of compositional sound. We can sort of neglect this, as has previously been done in the literature. But once we hit these supercritical conditions where exhaust is near the sound, where exhaust exceeds the sound barrier, the amplitude of this compositional noise, even scaling or accounting conservatively for the how strongly the mixture composition is varying in the nozzle, we're starting to generate appreciable compositional noise. This is on the same order. It should be considered in addition to entropy noise. And then lastly, we can see that for military jet applications, where you have a standing shock wave sitting downstream, you can produce up to 5 times as much compositional noise as you do entropic noise, which shows that this is really an important mechanism in these kind of shocked nozzle systems. So we demonstrated that this composition noise exists. But we also want to look at its sensitivity. We want to understand where it comes from. So if you guys were paying attention in thermodynamics a long time ago, the source term for this, psi here, is what we term a normalized chemical potential gradient. And basically, this is a function of the chemical potential, or the Gibbs free energy. To be a bit more intuitive, at least for the combustion folks in the crowd, it's a function of enthalpy and entropy, essentially. So we have the chemical potential, and then we have how strongly your composition is varying in species space. This is admittedly a bit abstract, so we did some simple experiments that would sort of qualitatively demonstrate the sensitivity to this mechanism as well. First, we considered a binary mixture composed of argon and then a second gas which has the exact same properties as argon, except we're going to vary its molecular weight. And what we can see here is that as we vary the ratio of the molecular weight, so if the second component becomes much lighter than argon, or if the second component becomes much heavier than argon, then we're going to increase the acoustic sensitivity, or we're going to generate more noise. So the takeaway from this is really that molecular weight is an important driver of this compositional noise mechanism. The second effect that we looked at is chemical structure. And the way we did this was by comparing 2 species which have identical molecular weights. So we picked argon, which is a very simple noble gas chemical structure, and we compared it against alene, which is a combustion intermediate, but it's basically just important in that it has the same molecular weight, and you can see that the bond structure is much more complex. And what we can take away from this comparison here is that if we have that when we introduce alene into the mixture, or an alene air mixture, the acoustic sensitivity is almost an order of magnitude. It's almost 200 to it's almost 2 to 5 times stronger than the response to argon. And what this means is that if you have a lot of internal energy, if you have a very complex chemical structure, that you have a much stronger propensity to generate this compositional noise. So the takeaway here is really that molecular weight and chemical structure are sort of the 2 driving effects to this noise mechanism. And now lastly, we're going to move downstream, and we're going to try to put this all together. So we started in the combustor, we moved through the turbine, and now we want to talk about sort of this nozzle, jet, and the far field, what you guys ultimately will hear on the ground. And to do this, we want to incorporate what we discussed in the previous chapters. So we can account for what's going on in the combustor using those databases, or that unsteady perturbation or fluctuation database from LES. We can combine this then. We can apply the low order models we had to account for the impact of the turbine for indirect noise generation. So we can take what we did in the second portion of the work. And then lastly, we can combine this. We're going to send this out through a jet. We're going to use large eddy simulation of a nozzle jet system to predict how much noise, or what the effect of these upstream perturbations is on total downstream sound. So to do this, we did sort of a very simple numerical experiment. We considered 2 different LES runs of this this nozzle jet system. First, we considered what I'm going to refer to as the unforced case, which is sort of a traditional jet exhaust simulation, where we have very clean inflow entering a nozzle. It's going to advect through, be accelerated, and then we can predict the far field sound associated with this. This condition corresponds to an experimental database, so we can establish the ability of our numerical framework to predict downstream sound. And then we can compare this unforced case to a so-called forced case, where we impose the perturbations that we got from the combustor and then amplified with this actuator disk theory, and we can relax them upstream, or we can impose them into the upstream boundary of this simulation. So that'll be our forced case. And then we know that any differences in the acoustic spectra between these two cases are going to be attributable to the presence of this forcing, or the sort of the impact of core noise on jet noise. So to do this, we picked a jet operating condition, which was thermodynamically consistent with our upstream simulation, and also corresponded to an available experimental database. Specifically, this corresponded to test point 49 in TANA's acoustic database. So this was some jet experiments that were done in the 70s and then were repeated at NASA in the 2000s that we can validate our flow against. What's important in the aeroacoustics community here are the Mach numbers of the jet. So the jet Mach number is 0.9 and the acoustic Mach number is 1.5. Temperature ratio is about 3, so we're accounting for the fact that we have heated exhaust. And then our Reynolds number is fairly large at just shy of 250,000. So we have this operating condition. We're then going to model this using large eddy simulation, in this case the code Charles. So we have a 25 million cell grid. Critically, we're sponging the outflow, which is traditionally done in these acoustic simulations. So having a sponge region on the outflow of the domain prevents any spurious reflection or artificial noise. But then what we're also doing that's novel here is that we're sponging the inflow. So it's truncated in this image, but upstream there's sort of a region of homogeneous pipe flow. And what we're going to do here is impose a sponge term that will relax or sort of impose these perturbation structures, these unsteady structures, so that we can get them to enter the device in a characteristically well-posed way. So we have this upstream forcing region that we consider. For the unforced case, we're forcing a homogeneous inflow. For the forced case, we're imposing these perturbations. And then lastly, we use what's termed a Fox-Williams and Hawking surface, which measures the sound sort of very near the jet, and then will allow us to predict the far field noise associated with this. So we can take the noise along this yellow surface shown here, and we can project what would be heard a far distance away from the jet. So next, we can validate the unforced case to make sure that we're predicting the acoustic behavior accurately. So we begin by looking at the hydrodynamic field of the jet here. This is showing the axial velocity along the jet center line here. And you can see that our prediction, which is the solid line, is spearing the dots taken from the NASA Glenn data set for both the mean axial velocity as well as the axial velocity fluctuations, URMS here for the bottom curve. In addition to that, we can assess the acoustic performance of our simulation. So we're going to look here at first the directivity. So for those of you who are unfamiliar with aeroacoustics, the directivity describes the total amount of sound as a function of your orientation from the jet. So if this angle phi here is 0 degrees, that effectively means that in our coordinate system, you're positioned downstream of the jet exhaust. And then as this angle grows, you become sort of more perpendicular or more oblique to the angle of the jet. And you can see our data here are these red curves, and they're spearing these diamond curves taken from the Bridges data set. So we have a good acoustic prediction here across the angles at which sound is appreciable. And then in addition to this, we can look at the sideline spectra. So at a particular orientation from the downstream jet, we can take a look at the frequency spectra associated with the noise. And we can see that we're doing a very good job of capturing the sound at both 30 and 90 degrees up to this dashed line here, which is sort of the highest frequency that our grid can adequately resolve. So you're happy with the unforced case. We established the ability of our model to accurately predict the behavior of this jet. And now we can focus on the effects of this forcing and how it's going to alter this downstream signal. So just very qualitatively or very intuitively, we're showing the unsteady temperature field here. So you can see for the unforced case, we have very clean inflow that's entering this nozzle. Whereas for the forced case, we have those structures that we detected inside the combustor and then amplified with the low order model. And these are going to convect out of the jet exhaust and potentially change the acoustic behavior. So again, any differences here are going to be attributed to the presence of this forcing. So first, we can take a look at the hydrodynamic field associated with this jet. And what we see is that there really aren't very strong changes in the velocity field when we impose this jet forcing. So if we look at both the centerline steady profile as well as the fluctuating velocity profiles, there aren't really big differences between the solid symbols here for the forced jet or the open symbols for the unforced jet, there really aren't large changes in hydrodynamic structure which would suggest appreciable changes in the acoustics of the jet. We do notice that the forced jet, the potential core decays just slightly faster. It's I think a little less than half a diameter. But there aren't major changes in the hydrodynamic field. But if we instead look at the acoustic field of the jet, we start to see some important differences here. So we're going to begin with the directivity plot, so the sound that you're hearing is a function of your orientation. And we can see that at low angles, or relatively shallow angles, where the noise is loudest, we see about a 2 to 3 decibel increase in overall downstream sound. And in the jet acoustics community, 2 to 3 decibels is a big deal. It's in this seminar, it might be the difference between me being loud and me being soft, but for jet acoustics, this is an appreciable difference. And then at very wide angles, we start to see a very subtle, about order 1 dB decrease in the total SPL downstream. But if we look at this in a bit more detail, if we look at the frequency spectra at 45 degrees, where this noise is roughly loudest, we can see that there are sort of 3 different things going on here. First of all, we see a clear increase in low frequency noise. So this plot is shown as a function of Struhal number, which is sort of a non-dimensional frequency. And we can see that for low frequencies or low Struhal numbers, this red curve, or the forced case, is sitting above the unforced case. At moderate Helmholtz numbers, so at Struhal near 0.3, jets are known to have an instability where they flap around, or they can be excited near this frequency. And we see an increase in tonal structures, which suggests that this mode is being excited at moderate frequencies, so that this jet is sort of more energetically flapping around when we impose this forcing. And then lastly, if we consider the high Struhal number limit, or high frequencies, we can see that there's a slight suppression. But we want to be a little bit suspicious of this, because this is a relatively modest difference. It's maybe half a decibel. But we can examine sort of the persistence of this effect by conditioning that directivity plot on the Struhal number. So what we can do is we can take this directivity plot that we were showing previously, and now instead of considering the whole signal, or the whole spectra of noise that's being produced, we can look at a conditional signal instead, where we only consider the low frequency contribution to this plot, or we only consider the high frequency contribution to this plot. And what we can see here for the low frequency plot, this is exactly what we expected. So core noise is typically characterized as being very low frequency in nature. So if we impose these fluctuations, they have such a long wavelength that they effectively don't see the nozzle. They're going to radiate outward, and we see a clear increase across all angles, or all orientations, in downstream noise. So this makes sense. This is sort of what we expected. If we hadn't done the experiment, I'm sure Matthias could have told you this is how this would turn out. But what's more interesting is that if we look at the high frequency noise here, we see that there's a persistent, it's a slight, but it's a persistent decrease in the amount of high frequency noise that's being generated. And this suggests that sort of the structure, or the kinetic energy dynamics of the jet, are being altered by the presence of this upstream forcing. So to investigate this a little bit more, we looked at POD of the pressure field associated with the jet. So proper orthogonal decomposition is a modal decomposition method which will sort of optimally or efficiently characterize the fluctuating energy, or the temporal variation within a data set. So we can see, first of all, that if we compare the modal structures that this procedure identifies, that they're different between the unforced and the forced cases. In the forced instance, we start to see a wave packet, or this modal structure, that's much more excited very early in the shear layer, whereas for the unforced case, we see a much more broad, or more distributed wave packet for these principal modes. But what's really telling, or what's really interesting, if we compare the modal decomposition of the unforced case to the modal decomposition of the forced case, is that the amplitudes associated with the first pair of POD modes for the forced case are much more excited, or are much more energetic than the corresponding modes associated with the unforced case. So if we think about what POD means, this is sort of what this indicates is that using only a few POD modes, we can more accurately, or we can more completely capture the unsteadiness, or the fluctuations inside the pressure field. And what this suggests is that the unsteadiness of the forced case is in some ways more coherent than it is in the unforced case. It suggests that that large-scale structures, or sort of more orderly distributions of fluctuating energy, exist in the forced case than they do in the unforced case. So we see for these modes typically occur in pairs. So we can see for this first set that we have almost a 2x increase in the modal amplitude associated with this first mode. So it's much more orderly. And then this difference is made up over the remaining modes, so that the energy between the two cases can be normalized. So this in turn, coupled with that excitation that we saw at moderate frequency, suggests a mechanism in which core noise is modulating jet noise. So what we think is happening, or what the data supports, is this theory that we have these fluctuations in velocity and temperature, et cetera, that are entering the nozzle. They're going to come in here, and they effectively are sort of broadband. They're forcing the flow through the nozzle or the flow through the jet in a broadband way. And what this means is that there's more energy to excite the jet, that this jet is going to sort of flap more emphatically or more energetically, and that we're going to have sort of stronger, large-scale structures, or these paired rollers that exist in the shear layer. This in turn means that the behavior of the jet is going to be much more laminar than we would encounter in the unforced case. And this has implications across the range of spectral structures. So you see, first of all, that low frequency noise is going to enter this device. It's going to propagate through. It effectively doesn't interact with the jet. But then this broadband forcing also contains structures that exist near sort of the preferred frequency or the preferred oscillation frequency of the jet. This is going to excite them and promote these tonal structures that we saw in the moderate Strouhal number regime. And then lastly, what we observe is that if it's been shown in the literature that if you excite these large-scale structures, or if you have a more orderly velocity or more laminar-like velocity field inside your jet, this in turn is going to suppress fine-scale turbulent structures. Your jet is going to behave sort of as though it were more laminar than it would in the unforced case. And this in turn will suppress these fine-scale structures which are associated with high-frequency noise, which explains why we see this 0.5 to 1 dB decrease in high-frequency noise across the range of directivity. With that, I can summarize and conclude. We can go through what we've seen today. So first of all, we've demonstrated that large eddy simulation has the ability to replicate both the acoustic field inside an aircraft engine combustor, as well as to produce these representative turbulent structures that can give rise to indirect noise. And using this data, we built a library that allowed us to study the downstream effects of sound. Next, focusing on the turbine, we extended the predictive abilities of existing theories, namely actuator disk theory, by, first of all, accounting for frequency-dependent or geometric effects in turbomachinery systems or in flows with mean curvature. And then secondly, we demonstrated that fluctuations in mixture composition or equivalence ratio are a second but important source of indirect noise in these turbine or nozzle flows. Lastly, we employed actuator disk theory as sort of a low-order tool that allowed us to map this perturbation library coming off the combustor to the corresponding signal that we would expect to see coming downstream or coming off of the turbine. And then we can use this to study the implications of core noise on the far field. So we showed that if you impose these core noise fluctuations or you impose these unsteady structures upstream, they're going to modulate the noise levels associated with the jet across the entire frequency range. We see the increase in low frequency noise. We see improved excitation of moderate frequency structures, or sort of this preferred flapping mode of the jet. And then we see a mild to moderate suppression of high frequency noise associated with these core noise effects. And lastly, we proposed a mechanism which sort of accounts for this or explains the physics that goes into that. So now, before I take questions, first I just want to, So published work or results that came out of this. We have multiple refereed publications. There are some things that are still in press or in preparation as well. And then we have conference papers as well. But before I take any questions and we wrap up the talk, I just want to acknowledge some people who really helped me along the way. First and foremost among these is Matthias, who's really guided me since my first year here. He's been a great advisor. I've learned a lot from him. I know that I wouldn't be standing here today without his help. Also Parviz, who sort of played a sort of kind of a secondary role in my experience, but has really helped me, got me set up when I first came here to Stanford, and has really seen me through along the way. And lastly, the other members of my committee, Dr. Mani, who graciously agreed to step up in a pinch today, as well as Dr. Lele and Catherine for chairing. So I wanted to thank you. The admins here at CTR, Rika, Marlene, Rosa, Susan, Corinne, Pamela, everybody who's just made it very easy to be a graduate student here, facilitated whatever we needed done. Similarly, V, who I think has built a new machine for me pretty much every year of my PhD, who's live streaming this for me right now, so thank you. And Steve, as well as Mike Coyne at Los Alamos. My collaborators throughout this, I've had a lot of help throughout this experience. Javier, who's sort of the first person I worked with very closely here at Stanford, and Zhongle, Luca, Friedrich, Dr. Hamilton, Alexi, everyone really helped me get to be where I am right now. My office mates, George, who pretty much showed me how to turn on a computer when I first came here to Stanford, as well as Chris, Tim, everybody, and really the whole CTR community. It's been a great environment to work in. I've learned a lot from all of you here, so I really appreciate that. Secondly, I'd like to thank sort of my outside of CTR friends as well. So some of you are here today, some of you are following the live stream, so hello. But really, you guys, you took a kid from Chicago and you've taught me how to be a Californian. We've run thousands of miles together. I really appreciate all the support. I appreciate you guys putting up with me talking about core noise as much as I do. You guys have been great. I've really enjoyed my time here. And then lastly, this is really, you guys may have known me for 5 years, or in a few cases 9. But this has really been a long journey from, it's not just my time here at Stanford. So in my family, we always take that picture in front of the bushes on the first day of school. And this September, I think, was our 21st time around. So I sent that to my parents. And I would not be standing here today without the love and support that my parents have provided, not just through my time here at Stanford, but really the whole time I've been alive. So thank you, Mom and Dad. Thank you. Thanks so much for coming. And with that, I'll conclude, and I'll take any questions if you have them.
Very good. So that's the open portion of the defense. This is, I hope you came with a list of questions. I think I see the first question there.
Yeah, this is a quick one that's just application-based. So early on you talked about how combustor noise is kind of acting as a tentpole in the overall acoustic signature.
Yeah.
And then the results you're showing at the end are showing higher noise in the lower frequencies and lower noise in the higher frequencies.
Mm-hmm.
So is that higher noise in the lower frequencies, is that in the part of the spectrum that's the tentpole for the overall?
Yeah. So the plot that I showed there is sort of, it's very qualitative in how it's produced, but it's trying to distinguish between the low frequency noise associated with combustion versus that associated with the jet.
Yeah.
A question regarding the effect of the turbine stages.
Okay.
So my question is, you model the turbine as a quasi-steady.
Yeah, so we assume that there's a one-dimensional steady base flow, and we're just considering weak perturbations that sit on top of that.
And what is the effect of the number of turbine stages?
So it's just going to continue to sort of amplify the sound levels. If you can apply sort of a high fidelity approach, I think LACO and a few others in Europe have looked at this. And they find that these models work really well for about 85% of the turbine. But then ultimately at the trailing edge, you can introduce shocks, or if you have sort of very high dimensional nonlinearity, then it can be difficult to address. But you can apply these models in conjunction, and they should work for a full turbine stage.
Jeff, I think if I understand correctly, you said that the noise was strongly dependent on the Mach number at the end of the first stage nozzle. Is that right?
So in that application, we're just considering one nozzle, and it's regardless of what mechanism you're looking at, whether it's entropy noise, composition noise, or just amplification of pressure waves. You're always generating more noise if you're accelerating the flow more strongly. Noise pretty much universally scales with Mach number in these applications.
It's got to be pretty rare in a modern engine to be supersonic inside the turbo machinery.
Oh, yeah. So in the turbo machinery, the case we were considering there was a subsonic turbine. So you can apply this in both a subsonic regime for turbo machinery applications or in a transonic regime for nozzle applications. But basically, the more you're accelerating the flow, the more distortion you have, and the more noise you're generating.
So, somebody else? No. So in a military engine, say, where the turbo machinery is going to be subsonic, but the nozzle is going to be supersonic, is all of the action there in the nozzle then? So it's or not?
I would say that most of the action is probably in the nozzle. If you really wanted to idealize the system, you could kind of just tear the turbine out, and you would get a realistic zeroth order prediction just going directly from the combustor to the exhaust state. But especially once you account for these Helmholtz number dependent effects, then you really want to consider the geometry. Sometimes what you'll see is if you have a particularly either good or poorly designed blade, you can get amplification or suppression of certain frequencies just based on how the structure of the blade is or how it interacts with the forcing frequency.
this. Let's finish here. Thank you, Jeff.